interesting. That is not
a good thing. All right, I don't want to do too much, but once you've done a couple of these problems, you start to get a feel for what. So if you look at the big ass triangle, I need to know something. I could figure out this entire thing. So let me give you the little layout of the outline of the idea. If I can get this whole side, right, and I can't let that go. Hold on. Okay, come on, Jeff. Use the straight line thing. There we go. If I can get this whole side, watch. If I get the whole side figured out. What's that? Timmy filled out a well? All right, sorry. Dog is commenting on my drawing ability. I appreciate it. So if I could get that whole side and I can get this little thing here, couldn't I then figure out this?
Sine of t.
If I get this whole thing, if I knew this was 30 and I knew this was 10, well, how long is this?
20.
20, okay. So, I mean, that's an outline of where you want to be, right? In fact,
Yes.
that's sort of like the end game. We're in the end game. No, stop. Now you got to take a step back and say, how do I get there? Well, this little dude is going to be easy. It's obviously probably not 10, right? That little dude will be easy because you know enough about this triangle. This is going to be the one that's a little bit tricky. It's obviously not 30, right?
Yeah.
Because you basically don't know shit about this big triangle, except the 26 degrees. But you do know something about this triangle that could maybe give you something about.
Yeah. Oh, okay. Okay.
That's awesome. That might be too much. That was too much. I should have stopped.
No, that was helpful. I spent like
Oh,
an hour on it before I went crazy.
That's too helpful. But that's sort of the approach to these problems. Is very often, this doesn't work for every problem, but I would go, man, if only I knew that, I could then get this. So I then go, oh, what was that thing I wanted to know? Can I get there from what they tell me? So it's sort of like starting close to the end. I would be done if I knew this and this. Well, can I get one of those things from what they tell me? It gives me a goal to work towards, right? And the thing we need to start realizing is sometimes that goal we set up is the wrong goal. And we'll notice that as we're working, we're like, I can't get that actually. So then we'll have to step back and think of another way. That's just a part of the process sometimes. Now, a lot of these problems have very kind of set ways to do them. You don't know what those are yet. So you're trying to figure them out right now. Let me see. Now, there's somebody else had a question. I'm going to stop sharing. Well, maybe not. Let me see if I can just see it. Here we go.
We're 5 minutes in the class time, by the way.
Oh, thanks, Jason. Let me see. I don't mind. We're fine. Let's see. Can you show another problem like 5 on the practice quiz? Also 66 on 7, 4. I used tangent with the 119 on the left line. Oh, I see. And ended up with the correct answer. I have no idea, Josh. Yeah, I'm assuming they don't mean this 119 to be this side. But if they do mean 119 to be this side, then this problem is easy as shit.
Cosecant of t.
So, I mean, I'll have to look at the solution manual. I have no idea. To me, if they meant this side is 119, they should have put the 119 here. Yeah, if you mean that I graded your work, it's very possible that I missed the problem. So, I don't know. How many questions did the quiz on? Somewhere between 3 and 80? No, I'm sorry. That's terrible. Actually, I know exactly how many questions the quiz will have, so it's not a question about do I think, because the quiz is tonight. So, I mean, tonight, tomorrow. I think it came out to be 13 questions, if I remember correctly. Lucky number 13. Somewhere around there. Total questions, right? A, B, C, D, E, F, G, H, I, J, K. Let me go back. So a problem like 5, I think I put, yeah, one bonus question on there. Yes. All right, let me do this. Let me stop sharing so I can just recollect my thoughts. So somebody's asking for problem like 5 on the practice quiz. Oh shit, what just happened? Holy shit. Okay, here we go. Practice quiz 7. Number 5. What was number 5? Load. There we go. Oh yeah. Oh yeah. Did you guys enjoy number 5? Number 5 is amazing. I will tell you this: the problem that is on the quiz is nowhere near as freaky as number 5 is on the practice quiz. So if we are recording, yes, we are. So don't, cuss or any shit like that. All right, we're recording, everybody. So just be on your best damn behavior. What was I saying? So I have a question for somebody to do. Somebody wants me to do a problem like number 5, the car wheel one. If you didn't try this one out, you missed out on a lot of fun. This problem is really awesome. But again, like I said, I'm not going to. So we did some problems about linear velocity and angular velocity, those kind of problems. We've done those. If you have a specific question like from linear or angular velocity, I could do them from the homework. The problem I'm going to give you is not going to be quite as multi-stepped as this is. There's quite a few steps involved in number 5. I love number 5. I don't know if that helps. If I have a more specific question, I can work with it. 66 on 7-4. Okay. Where are you? 66. Get down there. There he is. Oh, cool. I love it. All right. So here's the cool thing. I don't know how much you guys, I sort of skipped over talking about even and odd, not really on purpose. Well, I think I said something about this, didn't I? Maybe not. So cosine starts here, of course, and goes down and over and down. It's the little octopus dude. So do you guys remember, is that going to be even or odd for cosine?
It's going to be even.
There we go, even, yes. So it's remember, my most basic idea of even is x squared. Get down there, okay. So that means that it's got to mirror through the y-axis, right? The y-axis is the mirror, and that's exactly what's happening here. This is even symmetry. I like it. And then sine is like this. I don't know if you guys, oh, Jesus. Jeff, what happened to you? All right, it's fine. Do you guys remember? So odd symmetry is if it's symmetric through the origin. Oh my God. Okay. So if and that's such a weird, point symmetry is so weird, but it's basically if you draw a line through the origin, you get the negative reflection of that point. So that's odd symmetry. Now, I think of even as being positive and odd as being negative, because if I have even times odd, I get odd symmetry. And if you try it, what's x squared times x cubed? Isn't that even times odd? What's your result? Freaking odd, right? So even times odd is odd, and even times even is even, and odd times odd is even. All right. Is that enough, or is that still too weird?
Oh, is tangent odd or even? Like probably.
Say again. Say again.
Tangent, is it odd or even?
Yeah. So tangent is sine over cosine, so it's even divided by odd. And in fact, you know what tangent looks like, right? Doesn't it look like a cubish? So positive divided by negative is negative. Now, let me really make this clear. This is how I remember how even and odd symmetry interact through multiplication and division. I decided in my own head that even is like positive and odd is like negative. And then all the rules make beautiful sense. Even times even is positive. It's even. Odd times odd.
Sorry, I took over the kitchen table.
Sorry? What's happening? I'm going to mute you. I don't know what you're saying. Okay. So tangent, not only is it odd because we know that from the graph of it, but it's also odd because it's like positive divided by negative, which is negative. So odd. Let me stop for a minute.
Okay, and then how about like secant and cosecant?
Well, secant is 1 over what?
Cosine?
Cosine. So it's like 1 over odd. So it's 1 divided by negative is negative. So it's an odd function.
Oh, okay, I understand.
So that's how I remember that. It makes it so much easier. So it's not true in any real sense that odd is negative and even is positive. That's not true, but it's a beautiful way to remember how they interact. And again, if I have x to the 4th and I make a reciprocal function out of it, it's still freaking even, right? If I put a negative in there, it becomes the same thing as it was. So it's a reciprocal function of an odd function, so it's still odd.
Isn't cosine even?
Even. What am I thinking about? Thank you. I had the right example, and I was just saying odd. I don't know. All right. Is that help even with that last mistake there? Maybe.
So what does it mean if you're adding even and odd functions?
If I'm adding, all right, same thing. Now that's something we've done before. So for example, is this even or odd? Well, it's a sum of even functions, so it's even. Right?
So
Whereas
it's
this,
just kind of this. So it's just like the same rule then.
yeah, that rule has been well established. We just never really looked at multiplication or division rules until right now. And they do discuss this in the section. And I didn't necessarily skip it on purpose, to be honest. Okay. So if I had like, oh, I don't know, secant x times tangent x, is that even or odd? Well, one thing you can do, I'm sorry?
Is it odd?
All right, why do you say that?
No, wait, it's even because it's secant.
Yeah, so secant is like cosine, which is even. And tangent is sine over cosine.
Isn't
Right? So like,
secant odd because it's isn't secant odd because it's 1 over cosine?
yeah, it's 1 over cosine, and cosine is even. Cosine looks like this. So cosine is even. I did just have a brain fart in this area over there a minute ago. But cosine is even. Sine is odd because it looks like it has origin symmetry through the origin. So sine is odd. You guys all right? Okay. Maybe. The thing about even odd symmetry is the minute you have it shifted left or right, the whole thing goes to shit anyway. But yeah, and later you can talk about symmetry. Right now we're talking about symmetry only around the y and x axis and the origin, but you can have off-axis symmetry. Anyway, that's related. Okay. Anything else about that idea? Even and odd? Oh, wow. Yes, it has, so odd symmetry is officially symmetry through the origin. You can have different point symmetries, but we're not going to talk about this. The only point symmetry we've discussed is odd symmetry, which is through the origin. It could be on the quiz, but I'll just tell you right now, I didn't put this on the quiz. No. Somebody's asking, this will be on the quiz. I didn't put this on the quiz, so no. Does that mean you don't have to know it? You know that. You gotta know this shit. Okay, let me see. Did I miss any questions? Let me see. 66 on 7.4, is that the one I was looking at right now? Yes, okay, good. So it looks like I didn't miss any questions. Anything else, guys, before I get back into where I left off? Okay. Did everybody has well, the practice quiz is up there, the solution thing is up there if you want to look at those before you take the quiz. One thing I didn't think about on the quiz, I will allow you to, well, let's see. I don't know. You really should know these. The formula for arc length, you should know that. The formula for area of a sector, you really should know that. It's not that big of a thing. And beyond that, there's not much else to know. So I do have a portion of the quiz that says absolutely no calculator on this part. So I don't want to see any decimals on that part at all. Everything's got to be exact answers. Okay. What was happening? This is like, is today like random noise day? Is that not on my calendar? Okay. So, okay. So let's get back into where we left off. Let's do an example problem of graphing a sine or a cosine, and then we'll build secant or cosecant on top of that, which is not something we've done officially yet. Then we'll look at tangent real quick, and then we'll see what time it is. All right. So let's try, let me see, did I do any examples? Sort of, sure, you can try that.
It's out of frame.
Okay, okay, thank you. Oh yeah, I did boost it down a minute ago. Too bad. All right, so here's what I would ask you to graph this after finding the period, the amplitude. Did I make it? Yeah, I'm sorry. The phase shift. And then you could do the beginning and end of the cycle. So what's a really good first step to do with the function as it's given to me?
Pull out the half.
Yeah, back to the inside. All right, let me stop for a minute. Is that all right? If I divide something by a half, it becomes twice as big. That's 2 pi over there. So how do I get the period? What's the period of cosine normally?
2 pi.
Pi. And what's the value of k?
1/2.
1/2.
1/2. So what's the period going to be now?
4 pi.
4 pi. Which makes sense because that's a number less than 1. It does the opposite of what it seems. It's going to make it stretch by a factor of 2. It's going to take twice as long to get through a cycle. I like it. Okay. Amplitude's boring. What's the amplitude? Okay, thanks. That's 1. What's the phase shift?
Left 2
2 pi?
Yeah, so left 2 pi. I like it. And all right, this step is not completely necessary. You can also change it a little bit. It's still a good step to do if you're not really sure about what the hell's going on. I know that if the input of this is 0, it's at 1. And if the input of this is 2 pi, it's back to 1. That's the beginning and the end of the cycle, like a normal cycle, starting at 0. You could start it at negative pi, you could whatever. So that's the part that's up to you to change it if you want to. But if I just say, let me start it where the input is 0, and then I solve for x, right? Subtract pi, multiply by 2, I get negative 2 pi. Is that cool? So it's going to start at negative 2 pi, and it's going to end. And this is the part that's really not necessary because I know it's going to end 4 pi later. But let's just see if it makes sense. It should end at there. So when the input's 2 pi, so if I subtract pi, I get pi, and I double, I get 2 pi. So exactly what I expected. It's 4 pi apart. It should take 4 pi for it to finish the cycle. All right, let me stop for a minute. All right. Let me see, I got some new markers. Let's see what happens.
When you pulled out the 1/2, why did the pi double? When
So
you
real
put
quick,
1/2.
real quick, side note. How do you factor this? Just go ahead, I'm sorry. It's really stupid. Go ahead. It's really simple. You're gonna make a point. How do you factor this?
4 times x plus 2.
Yeah, you divided 8 by what you took out. Whatever you took out, you always divide by it, right? So if I am taking out a fraction, 8 divided by a half is 8 times 2.
Oh, okay, I understand.
Beautiful. I love it. I love it. It's that simple, but it's like we don't do that a lot. We don't normally take fractions out. Here I have to take a fraction out because I want this to be just x. But we're not used to doing it. I understand. I like it. So now, let's see. I kind of want to leave a little bit of space for some other stuff back here. Let's just go, yeah, I need negative 2 pi, that's right. That's why I want to leave some space back there. So we go negative 2 pi, pi, 0, pi, 2 pi, 1, negative 1. So I've got my normal 5 anchor points. My base anchor points for cosine are 0, pi over 2, pi, 3 pi over 2, 2 pi, blah, blah. That's the normal anchor points where it starts at 1, goes to 0, goes to negative 1. So now that all that's still going to happen is just going to happen across here, starting here. So it starts at 1, then it goes to 0, negative 1, 0, 1. Is that understood? I mean, that's on one level, it's like, it can't be that simple. And another level is like, what are you talking about simple? I don't know what the hell's going on. So I have no idea where you are with this. Let me get my little better blue there. Now be careful, don't just go, you know the shape of it is curve, 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 curve. Where would this be? push it out one more.
At 3 pi,
3 pi, I love it. Of course, this would be
negative 3 pi.
push it. All right, good. All right, and don't forget little arrows at the end, so I know that it's chapter. So I know that it continues on in that fashion. All right. Of course. Well, I'm going to take some stuff away here in a minute. That answers this question. Any questions from what we've done? All right, now, let me make some room. I'm going to take this away. This is old news. We already know all this shit. Go. We already know you. Just go. We know you. Go. Here's the beautiful thing. What if the problem would have been graph? Oh, do that, Jim. What if it was y equals secant of 1/2 x plus pi? If that would have been the original problem, I would have done everything we just did, except I would have made this dotted, because it wouldn't have been the answer yet. So that is the answer to this. So if the actual question would have been graph secant of that, let me just make it really difficult for you to take notes on this. I'll just erase that. It's my goal in life, apparently. That's not the right answer yet. Where will my vertical asymptotes be for the reciprocal function of cosine?
Doesn't it have to be all positive?
No, how do you mean?
I'm sorry, I thought secant was 1 over cosine.
It is.
So because it'd be in the denominator, doesn't that mean that all of the x asymptotes would have to be positive? No, never mind. I'm gonna shut up.
I think, so this is where it could get dangerous. I didn't even consider this. Are you thinking about the way I look at symmetries? All right. So maybe that was a bad idea. Even and odd do not mean positive, negative. It was just a way for me to remember even times even is even, because positive times positive is positive.
I think
You
she's
understand?
trying to say, like, if you have 1 over x plus 2, you know how you make x plus 2 equal to 0 because it has to be.
Yes.
Yeah,
Yes. Okay.
that's what he's trying to say. Is like if you were to put 1 over cosine, wouldn't it have to be positive since cosine is in the denominator?
Wouldn't what have to be positive though? I don't understand.
The x values.
No. So where is cosine 0? We can see it. Where's this function 0? Where?
Negative 3 pi, pi, negative
3
pi, and 3 pi.
negative pi, and 3 pi. Right? So this is 1 over this. So wherever this guy's output is 0, this guy's output will approach infinity. Does that make sense? If secant is 1 over cosine, wherever, in fact, I was hopeful for a minute when you're saying that. How do I find this guy's vertical asymptotes? I set the bottom equal to 0, don't I? And I find where that is true. The bottom is 0 and negative 2. Well, here, where is the bottom 0 for secant? Where is the bottom 0? There, and there, and there, and there. So that must be where there are vertical asymptotes. Does that make sense? That perfectly matches up with what a vertical asymptote is. It is those values that make this undefined, which in this case is what makes the bottom 0. I still don't quite see what the confusion is about positive and negative and all that stuff.
Yeah, you can't just look at the 1/2 x plus pi. You have to look at the whole function as equaling 0.
Yeah. In this case, this thing doesn't mean shit at the moment. because I've already taken care of what they mean. Go ahead, sorry.
Oh, I just think that the confusion could be that with square roots, you have to have a positive number inside, but with fractions, you have to have it can equal 0. I don't know. I just sometimes, I don't know if that's confusion or not, or.
I don't know. Maybe. I don't know. I don't know what the real confusion is. I'm really sorry. I don't know how to explain it because I'm not sure what it is. There's no radicals involved here. Any function that I have, what's on this side? All right. If somebody gave me the graph of a function, and they said, okay, 1 over this. Here's f of x. 1 over f of x. Can you find all the vertical asymptote locations? Well, what do you ask yourself? Where's the bottom 0? Well, it's 0 there, so there would be a vertical asymptote there, there. Yeah, maybe. So the nice thing is, the normal extra work crap that we have to do is because we don't know all the values of the function. I've got the values of the function. I've got them. I already plotted out the values for the denominator of this. I got them plotted out. So when I ask you, well, what makes this undefined? When's the bottom 0? I can just see them. I can see when the bottom is 0. It's staring me in the face. There's no work to do. I've already done the work. I've done more work than we normally do for this. And the reason I've done more work is because, watch this. So over here, maybe this is what you're talking about. Maybe you're like one step ahead, which will be awesome. Let's see if we match up here now. All the values here are positive. So what kind of infinity is it approaching as it approaches pi from this side? It's positive all the way, so it must be approaching
Positive infinity.
No, same thing over there. So that is a part of the answer. That's the part of the secant function. They look like cups sitting on top or hanging down below. So here, all the values are negative. So as I approach pi from this side, it's going to be going to negative infinity. And then the same thing happens over here. And of course, it keeps going in both directions forever, repeating this shape. That is a visualization that is so cool. This is the reciprocal function of this. These are the reciprocals of these. Since this goes between -1 and 1, right? -1 to 0 to 1 basically is kind of like the extremes in the middle. That means that this is going to go from 1 to infinity and -1 to negative infinity because the 0 makes it go to whatever infinity. I don't know how else to say that. So please do ask more questions. I want to find out where it is, where's the disconnect. If you can consider how to put the question together. So if the question would have been this, I would have done all the work we did. I would have done all the work for this, and then I could just draw these sitting on top and below that. That's kind of nice. So if the question would have been cosecant, I would have done the equivalent sine and then put the stuff on top and bottom of that. It's almost too nice.
So if it was secant or cosecant, you wouldn't ask for like the period, the amplification, phase shift, beginning, end, right?
Yeah, it's interesting. There's no true amplitude for secant and because it goes to infinity and negative infinity. There's some weird inner amplitude though, isn't there? There's some weird like amplitude until it starts, right? So if there would have been a 2 here, it would have been at 2. Doesn't mean the amplitude of this function would have been 2, but it would have started up here at 2. and it would have started down here at -2. So you're right. There's no true amplitude for secant or cosecant because they go to freaking infinity and negative infinity. There's no limit. They have kind of an inner limit, though. They can only get so close to 0. They can only get that close to the midline. So it's sort of a reciprocal relationship there because it's a reciprocal function. Is that all right? You guys doing all right? You don't have to lie to me. It's okay. I can take it. All right. And like I told you, if there was like a +1, right? Somebody brought a friend. No, if there was a +1 at the end, I would have drawn this and I would have just shifted all the points up 1, and then I would have done the rest of the shift. That is the last thing I worry about. I don't worry about it at all until I'm basically done, and then just shift all the points up 1. So would the range be all real numbers? No. That's a really good question though, Brian. That's almost not really right now. What would the range be of this? What's the range of this function? Looking at our results. Remember, this dotted line is not the answer. These are the answers. What's the range?
Wouldn't it be -1 to -infinity united with 1 to infinity?
Stop. It's always small to big. So it'd be -infinity and -1. Actually, that would be inclusive, right? Union with, yeah. 1 to infinity, yes.
Oh, makes sense now.
The one place where cosine and secant agree is there because 1/1 is 1. So that's the one place they agree. Otherwise, they are completely opposite-minded. Oh, all right. Let's see. Okay. All right. Just trying to catch up on all my little chat messages. So again, if everything was cool with this guy, and I didn't hear many questions about when we graphed the cosine, then doing this is just that one more step. Just putting in the asymptotes and drawing in the cups. Okay. Now, don't these look a little bit like little parabolas? Why are they definitely not parabolas? Why are they definitely not parabolic? Does a parabola have any constrictions in this direction? No. Do these? Yes. Right. So they look parabolic in a certain way, but they are definitely not. And one thing you would learn in calculus is how to determine the curve, the curvature of a graph. And then you can compare the curvature of this with the curvature of a parabolic graph, and you can see the difference. Yeah. Okay. Enough of that. Let me see. Let's do a let's try a tangent problem out. Now somebody had a really good point about secant and cosecant not having an amplitude. And I basically just gave away the answer to this. Will tangent have an amplitude to discuss? Let's do this. Let's remember the base function first. Let's do the base function first. All right, so the main thing is, what's the period for tangent? Unshifted.
Pi?
Yes, it's pi. I like it. Period is pi. There is no amplitude because, of course, the basic shape of it is going to be this, repeated forever in both directions. Now, where's it start and end? Where's like the core cycle? I don't know how else to say that. Core cycle, start and end. And one way you can consider this is, where would the vertical asymptotes be? And so that's what we did last time. Where are the vertical asymptotes for this? It's going to be anywhere that, what's on the bottom of tangent?
Cotant.
Cosine.
Cosine, right? Tangent is sine over cosine. So wherever cosine is negative, is 0, tangent will have a vertical asymptote. So where is cosine 0? Negative pi over 2, pi over 2. Is that right? Like a 90 degrees and negative 90 degrees, because that's where there's no x piece. It's all y. So cosine don't like it there. Don't really like it. So the regular tangent is going to have a vertical asymptote here and here. And of course, it's going to have an infinite more. It's going to have another one at pi over 3 pi over 2. It's going to have another one at negative 3 pi over 2. Forever. We normally just graph one cycle and then say it repeats forever. And we already did this. Remember, at pi over 4 is where it's 1. So it's negative 1 there, positive 1 there. It's 0 at 0 because it goes like sine. And as it gets closer to this, it gets more negative. So that's why it looks very much like a cubic. And then, of course, it repeats and repeats. And so let me stop for a minute. We did that already. Just want to remind you guys, before we start messing with this thing, all right, I'm going to erase all this. Here we go. So what if we had this? Let's see, what's a good one? Sure, why not? So let's see, let's start with period, phase shift. So I can do my regular thing here. What happens? What do I take out?
Pi.
Pi. And then I'm just left with, I just lose all my pi in there. All right. So far this feels the same. But now to figure out the period, the one difference, of course, is I'm working with a tangent. So what do I divide by? The k. What's the regular period?
Pi.
Yeah, pi. And then I divide that by the multiplier, the same as before. It's the same exact effect. Because whatever is here has the same effect on whatever function it's in. Whatever the multiple of x is, it's going to have the same effect no matter what the function is. Compression, elongation, all that kind of shit. So the normal period is pi divided by the multiplier of pi. Now my period is 1. And what's my phase shift?
One half to the right.
Good. So right, 1/2. I like it. So again, the more you do this, the more you're going to see that these are not really necessary, but they're nice to kind of hold on to for now. So where's it going to begin? So remember, this is where you got to remember what the basic tangent looks like. It's negative pi over 2 to pi over 2. It's kind of like where the normal little core cycle is. So I want to know, when is the input equal to negative pi over 2, and when is the input equal to positive pi over 2? I really want you guys to understand that when the input is negative pi over 2, there's a vertical asymptote. When the input is positive pi over 2, there's a vertical asymptote. That's all I'm doing here. Is saying, where did those asymptotes move because of all the shifting this crazy dude is doing? And the first thing I notice in both of these is, all my pi's die. Pi. So I get x minus a half equals negative a half. So that's x equals 0. Is that cool? And then here, these combined forces and make a full pi. All my pi's die. So I get x equals 1, and that matches up with this dude. My period is 1. It's exactly matching up here. So again, this is kind of nice because it verifies this. You can see it. It gives you an idea of where to start and where to end on your picture. So let me do this a different color. I don't know if this shows up as a different color. Use red. And then, so how do you illustrate this? Well, all you do, get out. So here's my vertical asymptote and my other vertical asymptote. So here, let's go and put 1/2 in there. Let me stop for a minute. So remember, the normal tangent at the pi over 4 position, that's where it goes to 1 or negative 1. That's where sine and cosine are equal. So that's what happens right next to the vertical asymptote. So that's where it would normally go to negative 1. But because of that, it's going to be at negative 2. And then it goes through 0. And then at this, it goes to 2. So really, that's all that guy does, is it does stretch it, but it doesn't really become that different. Hell, I could have just called this frickin' 2, and it would have looked the same as it always would. So now I just put in there the shape of it. It's a little too elongated for me. Get it. I like it. So you do want to. Where are my flashcard students at? Is anyone big into making flashcards? Or I don't know how you guys study. Me, I would just write something over and over and over again. And then I would never have to look at it again because I'm like a kinematic learner. I have to write it and it goes in my head. And then I never look at it again. I don't have to look at my notes again if I write them 4 times. I'm like, it's in, I'm good. You do have to remember these basic things about each of these functions. Tangent is from negative pi over 2 to pi over 2. What's cotangent from? Where it's like base asymptotes at. Does somebody remember?
Negative pi to pi?
No. Because one thing is, that it's going to have a period of pi. So think about it. Even if you don't remember, you don't have to memorize everything in the world. Cotangent is cosine over sine. Well, that you got to know. Where is sine 0? Where is sine 0? What angles? Another way to say that is?
Isn't it 0 at 0?
0 and
Pi.
I like it. So for cotangent, so this is the unit circle, all right? Cotangent is going to have an asymptote at 0 and pi is the main one. And then it's going to look like a reverse cubish. Now again, you don't have to memorize everything. You don't. But you do have to figure out, what am I going to memorize? And what am I going to use some way to get it? So I don't have tangent values memorized. I use sine and cosine to get my tangent when I need it. right? So that's the decision I made. So I'm not going to make every decision for you. I am going to give you ways to memorize things easier. I am going to give you how I look at things, but you need to make this your own. You need to make this your own. So if you have a way and you're not sure if it's true or something, you can always ask me. I'm going to remember it this way. Does that work? I can tell you if it's going to work or not. And if I like it, I'll steal it and use it myself. Why not? And then I'll show everybody. And then whoever likes it can use it for themselves. Who cares? Okay. Man, I really need to get to a real, I can't wait till I'm not cutting my own hair. That'll be awesome. All right. Let me see, what time is it? All right. I don't know. Do you guys want to do another example of this, of graphing some trig function? Or do you want to do something different? I'll leave it up to you. It's one of those two. There's no third option that we leave class right now. That's not just to circumvent anybody. All right. So I got somebody. Can you be more specific? Another example of what type? Cosecant. Ooh, I like it. All right. So let's do, I use f of x just to change things up. Cosecant, let's do 4 cosecant. Oh, which got Jeff? I don't know, man. Let's do 2x plus 1. Yeah, I don't even care about this. Well, sure, let's, why not? We haven't done one yet, Jeff. Why not? So much shit happening in this problem. All right, so I'm never going to give you a problem and give you no prompts. I'm never going to say, graph this, good luck. So I am going to ask you, what's the period? So I am going to prompt you along the way. So what am I going to graph first? I'm going to pretend like what's here?
Sine.
Sine. I'm going to pretend like that's a sine. And because then the cosecant is just drawing the little u's up top and down below. So period, amplitude, phase shift. So I will ask you for these. So what will our period be? How do I figure it out? What goes on top for sine? What goes on top for the period for the sine?
Is it pi?
No, that's tangent and cotangent. So tangent and cotangent have a period of pi. Sine and cosine have a period of 2 pi. So this will be the normal period divided by what? I haven't even factored the inside yet, but I can see what's going to be.
2.
2. So our period now is pi. What's the amplitude?
4.
4. And if I don't even really have to factor this. I mean, if I did, I'll get that. But I can already tell what makes the 0 is -1/2. So it's been shifted 1/2 to the left. But I can see it. I can just see it if I do factor. Left 1/2. Right, let me stop there. So these are the definite things I would ask you for. I'm also gonna, if it's a cosecant problem, I'd also say, you know, identify your asymptotes. But you really, there's no other way to graph it if you don't do that. So we're going to get the asymptotes at the end. And now if you want to, you can do the begin and end. So if I take the inside and set it equal to 0, and I take the inside, set it equal to 2 pi. Oh, this is gross, isn't it? Well, it's too bad for us. I didn't want this to be this gross. All right, let me change it a little bit. I'm never gonna make one this gross. Let me see if you guys, I don't know if you guys can see why this is gonna be a little gross. Do you understand how this is gonna make the scale? If I subtract 1 and divide by 2, x is gonna be 2 pi minus 1 over 2. Not the best scale. So in real life, it could be any damn thing, but then in real life, you're gonna have freaking graphing utilities. Who cares? But for a problem you gotta do by hand, I'm gonna try not to let that happen. So let me change one thing. Let's make this pi. Okay. So what does that change? Doesn't change this. Doesn't change this. Does change this. And now, this will be better. It'll be purely in terms of pi. So my scale, normally for these problems, are going to be purely pi, like pi over 4 and all kind of, or purely integers or, or rationals, 1/2, 1, 3/2. Not a mixture, that's disgusting, or by hand. So here I get x is negative pi over 2, so it's going to start at negative pi over 2. And here I get pi over 2. Does that match up with my period? Yes, because these are pi apart. I love it. So yes. Some of you guys might realize it's left pi over 2, which means it starts at negative pi over 2, and then you just add pi to it to see where it's going to end. So that's why I keep saying this is not really necessary to do like this. So now I got to remember to do a dotted line for my sine, because the answer is going to be the cosecant, the cut parts, the up and down. So what does sine do? At 0, sine has what now?
0.
0. I love it. Let's see. Sure. So it's going to start at 0. Then it normally goes to 1, but of course now it's going to go to 4. So yeah, it starts at 0. Then it's up at the maximum. Then it's at 0 again. Then it's at the minimum. Then it's at 0 again. And now there's another dimension. All right. So I've got enough here to see several vertical asymptotes. That's going to be good. So let me do this real quick. So now I'm going to build off of that. I'm going to build my secant. Where are my vertical asymptotes?
Don't we have to shift it down one?
Oh shit! I forgot I added that in. Thank you. That's going to be, yeah, that's still going to work. I didn't think ahead too much, but it won't. So we have this guy that I decided at the end there to add in. So that's the last thing you always do. That's always the last shift you do. So now every point just goes down 1. Yeah, my scale is the same. So this point goes down 1. This point goes down 1. This point goes down 1. So now it's like that. Well, you might even want to erase the original one, just so it's not too much shit happening. All right. So I sometimes have students that do maybe a couple of graphs or something. It's up to you. Or multiple colors, whatever works better. Is that going through the right thing? Little dude. So now I can put my little cups on the top. Where's the vertical asymptotes? Now it gets interesting. Well, the vertical asymptotes are going to be where this guy is 0. So it doesn't involve, so it's still going to be where these originally were. Does that make sense? Because if I move it down 1, the vertical asymptotes don't give a shit. They're still going to be where it hit the 0 before. So it's going to be there, there, there. Oh, I was going to do that in red. Too bad. And then I just draw in, these are the positive values. Here's the negative values. And make this, yeah, that's good enough. So that's a complete cycle for cosecant. Because then it's going to repeat that shape forever in both directions over there. Okay. So it really is, whenever you have a secant or a cosecant, you just pretend like it's, just do the graph of the original function before you do the reciprocal function. This does not affect where the vertical asymptotes will be, because it's just going to move an infinite line down 1, so it's still an infinite line. And how can you check your work? Now here's something interesting. I haven't talked about this yet. Do you have a cosecant function on your calculator? Let's look at the calculator real quick and see how the hell would I check this work. So let me open my calculator. Where are you? There you are. There he is. Come on. Hello. All right, so let's take a look here. You out of the way. Okay. So all I see are my sine, cosine, and tangent. I also see, what are these above sine, cosine, and tangent? What are these?
Aren't those basically the same? Because sine to the negative first is just 1 over sine.
No, careful. No. So, hold on just a second. I'm going to stop sharing. F of x. How would I represent the inverse of f of x? What's that look like? What's the symbol for inverse of f of x? What do I put right here?
-1.
-1, there, yeah. So sine -1x is the inverse sine. So it's still just as evil as it ever was. This decision to make it a -1 power, so it looks like it's reciprocal. No, it's inverse. There's actually another name for inverse sine, and I just tell you right now, it's called arc sine. So arc cosine, arc tangent, arc cotangent. It's another way to say inverse, where you don't have to use that symbol, so you don't make the mistake of thinking it's actually cosecant or something like a reciprocal function. Are you guys still with me? So let's look back at that funky old calculator. So how the shit, if I wanted to graph the function that's up there, what would I put in here then?
You just do 1 over sine.
Yeah, so the way it would go is I would do 4 times 1 divided by the sine, and then I would put the 2x, what is it? 2x plus pi. So that is 4 times cosecant. And then minus. All right, let's see what this does. I'm going to hit zoom 6. Look at that. That's awesome. That's kind of satisfying to see that happen. This isn't that great. Let me see a couple things. Here's something really interesting. Zoom Trig. See Zoom Trig? That sounds interesting. Oh, that's too funny. Now, look what it did, though. See how it can only see up to 4? And, of course, we know that this one starts at -5. So all I got to do, let me go in and change my window. Real quick, does anyone see what that is? That scale that's going by? Does anyone see what that is? 1.5707.
Is that like a half a pi? Something close to that?
That's exactly a half a pi, right? Half of 3.14 is 1.57. So whenever I get like a number at a deli, 157, I geek out for a minute and then I calm down. So that's what Zoom Trig does. It makes the scale correspond to pi over 2. What I need to change is my y min and y max. I want my y min to be more like -8 maybe. Well, let's make it the same as it, -6. And then oh yeah, Jeff, good. Well, this would be a good reminder. Hit go to when you make a dumb mistake like I just did. All right. And then y max, let's make, 4 is fine. So this maybe will match up better. Let's see, x min, our x min is like -pi over 2. So let's make this -1.6. That's a little more than -pi over 2. And our x max is pi over 2. So we'll make that 1.6. Why not? Let's see what this looks like. Cool. Sorry. I don't know if you guys understand why I'm excited. It's exactly what we got, right? I like it. Hey, Mikey. Now, I could change my scale to be pi over 4. So then, yeah, there 1. So then it matches perfectly with our scale here, right? You can see that. Okay, I like it. Okay. So anytime you need secant, cosecant, so secant would be 1 over this, cosecant or cotangent. That's how you have to do it, unfortunately. Yeah. So the next thing, now watch. What angle gives you a sine of, all right, now watch. Well, let me just say this. What angle gives you a sine of 1/2? Think about it. Where's sine smaller? Doesn't like it there.
Is it 30?
30. So like pi over 6, right? So watch this. If I do inverse sine, now what does an inverse function do? It takes the output of the original function as its input. So the output to sine of 30 or sine of pi over 6 is 1/2. So if I put 1/2 in here, the answer better be pi over 6, which is roughly a little over 0.5, right? You guys with me? Pi is roughly 3, so 3/6 is 0.5. So it's going to be a little over 0.5. There you go. If I did it in degrees, that would be even more interesting. There you go. That's something we can hold on to a little bit better, right? So those are equivalent. That's degrees and that's radians. Equivalent. I like it. So that's what we're going to get into next is inverse trig and how the hell can inverse trig exist when these are not 1-to-1. So that's what we were talking about before about restricting the domain. I love it. All right. But I think otherwise that might be enough for today. That's plenty. We got one more day. We can finish up chapter 8 on Monday. The quiz should be open now. If anybody wanted to start it like right now, you could. Otherwise, and let me know if you have any questions. Otherwise, the class is over for today. Have a good weekend.
Bye.
Yeah,
Thank you.
See you guys
Thank you.
anytime.
Professor, I have a question.
Yeah. Yes.
Can you explain one more time how did you get the period
For
for example the cosecant?
So since cosecant is 1 over sine, it has the same period as sine.
That's
So
sine.
you
Okay.
have that sine and cosine has pi, and tangent has pi. So they're reciprocal functions. So cotangent has pi also because it's a reciprocal of tangent. And
Okay. So and then the way you got it is just it's pi, so it's 2 pi, and then over 2 because of the 2 of the in front of the x.
yeah,
Or if
so
it's
it's always divided by that multiple.
Okay.
That's how much compressive, yeah.
Okay, and then you factor it out to get the phase shift.
Phase shift, exactly.
Yep.
Because I want to
Okay.
see what's affecting the x directly. That's why I got to get the 2 out of the way. So I can see what shift is happening to the x. Like,
Okay. Awesome. Thank you.
what?
Hi, I just had a question. I wanted to find out exactly what the quiz was on, and it was just all section 7.
It is.
I'm sorry. I had a week this week. Some
I understand.
family things came up.
Okay. Well, that part I maybe don't currently understand, but in general, I understand. You're fine. You got until tomorrow at 6. So you just gotta
Oh.
find.
Awesome, because I usually work from 7:30 to 4.
Gotcha.
That's awesome.
I gave like an hour and what was it? I can't remember what I gave. An hour and 50 minutes.
Okay,
So yeah.
awesome. Thank you.
Well, see you.
Bye.